Let's come to order, please. Yeah. All right, talk to me about this problem. So you can imagine the situation where Zach are dividing colored crayons between them, 15 all in total. It's a very exciting moment for them. And assume they're all unique crayons. Sorry if we didn't say that. Josh, what did you think about this situation?
I think it was like the order doesn't matter. Whether I think if 15 choose 9 or 15 choose 6, we feel like it doesn't really matter which one you decide on. Like the equation, like show. So
What's your calculation and what's your answer? What do you think?
I feel like it's like 15 choose 6 or something. It's like something like that. Because the rest of them just go to the first step, so it doesn't matter what they choose.
Okay, Kaylin, respond to that.
Oh, I just thought that it was 15 factorial because I thought of it as like if there are 15 like spots, like the 15 crowns, and then you split it up between Zach and so you're right. He's right. I just realized.
Isn't math wonderful? Does anyone else want to respond to the conversation? Yeah, Francis.
What I wasn't really sure about was if it's 15 choose 6 or 15 choose 9, because looking at logically, either the first Zach takes all 9, and then the rest chooses a random combination of 9, and then the other 6 are left.
Yeah, that's a good point. Is it 15 choose 9 or is it 15 choose 6? That's the important question.
Don't call on Katie.
I guess we'll never know what we should do on this problem. No one will ever know, I guess. Does not anyone want to contribute at all? Oh, Katie, I didn't see you there. Go ahead.
15 choose 9 and 15 choose 6 are the same thing.
Oh, they really?
Because, for example, we have 15 choose 1 and 14 are the exact same. They both have like the total numbers and the exact same.
Katie, I'm so tremendously proud of you.
So I think that in the end, let's just say this: Josh is right. It's just 15 choose 9. Okay. There's not a need to account for anything else. Like he said, there's a sense in which anytime you select 9, you're kind of also selecting 6, right? So those, in fact, do count the same thing. You can type in either one, Katie says, and in either case you get what number? Did you see? 5005. All right, and then Katie reminds us that actually we've kind of been making this observation already a little bit, seeing this kind of symmetry. Sorry, my voice is going. Be nice to me, okay? But she says, didn't you remember noticing this the other day when we were doing pizza toppings, or any other time when we were like, didn't we see that 15 choose 0 is the same as 15 choose 15? They're the same, right? They're both 1. 15 choose 1, 15 choose 14. They're the same. They're both 15. So it does make sense that this is the case. If Zach takes 9, Zach number 2 is like left without any choices in his life. Like the 6 have already been decided for him. It's over. So, well, it's not about these two Zachs.
Did you guys just realize that that's the first thing I called?
This is a hypothetical problem. It has nothing to do with all the names have been changed.
Zach, how many crayons did you get?
Are you the 9 Zach or the 6 Zach? We give them each 7 and break 1 in half. Okay. Any all right, this will maybe come up again soon. So just keep this harbored away in your heart, okay? Let's answer a question if there is one about the homework. If some of them are interesting, do you want to ask one question or two maybe?
Wait. I got a log. It's just 20, right?
Yeah, you might need a logarithm. Or you can just guess and check. We're not asking
What about this one?
Dina, tell me, remind me.
I don't know either.
Oh, come on, 17 math teachers. What was this one like? Yeah, like the warm-up. So you need to understand if we're clinking glasses, that's the same as the handshake problem, people will say, or hug problem or the key exchange problem, whatever you want to say, just like the warm-up. Yeah. The answer on number 11 is just 17, choose 2.
High five.
Some interesting problems on there, though, right? I like some of those. They're good. Any other ones you want to? Yeah.
What was 10F?
Oh, thank you for asking about 10F. Yes. So 10F is worth mentioning. It's probably the most intense computation on this homework. We are asking for exactly 7, or exactly 8, or exactly 9, or exactly 10 engineers. Isn't that what we're really asking? So exactly 7 is computed this way. There are 20 engineers, choose 7. But you also have to choose from for 14 non-engineers, 3. That's the number of ways of getting exactly 7 engineers and 3 non-engineers. But of course you can also get 8, that qualifies for this problem as well. And as laborious as this seems, this is in fact the only correct way to do this problem.
Wait, really?
There's no shortcut. Feel free to think of a shortcut that you think will work. Compute your answer, compute this answer, which this answer is clearly right. The logic is laid out pretty clearly. And see that it differs from other things you might try to calculate. Here 14 choose 1, of course, is maybe not worth writing. That's just, of course, 14. And this is really not worth writing, this last little piece here. Exactly 10 would be 20 choose 10, which is interesting. 14 choose 0. Is that even worth mentioning? Maybe not.
Yeah,
right?
because it's a denominator of 0, so it doesn't work. Oh.
I mean, 14 choose 0 is 1, right?
Oh, really? Never mind. Come on, guys. Sorry, go listen.
Yeah. Okay, that one I don't remember off the top of my head.
It's set exactly 5 engineers.
What is it?
It's like
Exactly 5 engineers, 2 managers, and 3
Good question, Dina.
Wait, 10B is what?
That's the one, right?
this was
So I think we just need to fill the 10 slots, right? So from the 20 engineers, from the 4 managers, and from the 6 marketer 10 marketers, choose 3. Multiply.
Is it
Yeah, Dina or who else? Kate. Someone. Yeah. Okay. So multiply those. It's like the pick 3 threes and 2 non-threes, or pick 2 women and 2 men for the committee. And we did some examples like that a couple days ago. All right. Well, let's switch gears a little bit. We're gonna actually step away a little bit from combinatorics today and do some algebra. Okay. So we're gonna talk about something called the binomial theorem and its applications. So we'll see what we can do with this.
Wait, what's the other thing binomial theorem?
Pretty sure.
that's the same thing?
So the task that I have for you right now, just to keep children out of trouble, is to do the following. Busy with. Are you ready? Okay. Now, some of you who I don't know, because you are on that team or because your dad told you or something, or maybe you already know, like a secret for this. You're not allowed to use the secret though. See if you can do it by hand. If you know what you're supposed to get, that's fine. But try confirming that is what you get by hand. So I'll do the first one for you. There you go. You're welcome. I can, yeah, so expand these. I mean, the first 3, of course, are easy. A plus b cubed is a little bit trickier, but take your result from a plus b squared, whatever that is, and multiply it by another copy of a plus b, right? And collect terms. Put back together the number 2. The first one, like I said, I did for you, okay? Trying to save you some time. You're welcome. I'm gonna give her.
There was a shortcut.
Wait, no, I didn't say anything.
Yeah,
Wait, I don't know if we're doing a shortcut.
well, don't try and move back to it.
What is this?
get a plus b cubed, let me know. I want to check. I want to see how you did. You got the.
I have no
I
idea.
mean, start working on a plus b to the fourth when you're ready.
I got
Wait, I'm not supposed to.
That says 0.
Oh, wait, didn't this one, what was it? This gets taught us this, and I forgot.
A plus b to the 0th is 1, right?
Right, so
Why does
Yeah.
that work?
I thought you said mathematics are lazy mathematicians.
At any point, you should feel the pressure in mathematicians to show you the reason.
I think I can do this. No. Yeah.
It's so easy to do that.
No, I'm not doing anything. No, I'm not doing anything.
Nothing. I learned those things
I'm not,
but I've learned more. No, I'm not exaggerating. I think I have like a general idea.
hey, you guys, I did see my eye on my
Multiply it times this. Oh, shucks, you have to do it long.
This. Is this my hand? That's not. Shut. What I got.
The front door.
Alright, wait. Wait, you're not gonna try it.
Dinesh is cheating short.
No, I.
Dinesh is cheating.
How is that cheating?
Because Mr. Chase said don't cheat.
I'm just using my. Okay, how about this? In the visualize
He never made it.
Oh, you have some classes. Yeah, you got it.
I'm not
Yeah,
very
sure.
No, you can't.
All right, I think everyone has the cubic one, right? Everyone.
Wait, give me
Dinesh and I are best buds. I just like being my own
But you can't simplify.
So I'll give you the next couple here. A plus b cubed, then remember, is just gotten by taking a plus b times this quadratic.
Looks like a fun.
What is the first thing?
Wait a minute. Is this gonna end up being something really obvious?
So a plus b cubed.
I know
I think most of you have a plus b cubed, maybe, right? I want to make sure everyone
I
tries that.
can't
one.
believe what it says. Oh, that is. Wait, where does it simplify? Oh, it's 3.
So a plus b cubed. Oh, we'll give it away. Hopefully everyone's had a chance to try it. And some of you even got to the a plus b to the fourth, or maybe even the fifth. I don't know. And I'll put those up here as well. Now let's see if we can notice a couple patterns. So first of all, in like say the a plus b to the fifth expansion, you see that all. Talk to me about the variable part first. About the variable part first. What do you see in terms of the variables?
They're all 5. Or no, they're all multiples of 5.
The variable part, a to the fifth,
wow,
a to the
I'm
fourth,
very
b.
smart.
Oh, wait. They add up.
Like
What?
when you add, when you like you start with the highest A, so like whatever the power is, and then you decrease one, so then you add a B, and then like you decrease one, like add another B, and then like.
Yeah, yeah. And what were you gonna say, Michael? Too?
They always add up to whatever your power. Like if you add up A and B, they add up to whatever your power.
Yeah, the exponents on a and b sum to 5 in that case, right? Yeah. And as Katie said, I think it's important to see that they walk down every version of a to the fifth and b to the whatever, you know, to add up. All of them exist in this expansion. We can write them down in order. And then, and then for those who haven't, I've heard lots of people mumbling about it, but for those who haven't seen it, let's highlight the coefficients in red. And I think even those who aren't like on math team or something like that have probably seen this before. It's what?
That's
Pascal's triangle.
It's like the 1, 1, 1, 1 plus 1. So that you have 1 on the side of it.
It remains to be seen, like, why does that work? That's right, like, why does this appear in this place?
I should have done that for my eyes. No,
I think
that's not it.
in mathematics we want not just revelation but illumination, so we'll try and achieve both here. But yeah, that's called Pascal's triangle. Like Katie said, if you take 4 and 6 and add them, you get this coefficient below. Like that, right? Have you seen that? I think we're ready to have the statement of the binomial theorem. Here it is. And there's one more surprise in the statement of this theorem waiting for you. This is not a surprise based on what Katie and Michael just said, that we have a to the n minus 1, b to the first, a to the n minus k times b to the k. In general, these two powers add up to n, right? That's not a huge surprise. Powers of a walk down, powers of b walk up. But the surprise that's kind of waiting for you on this slide and this statement of this theorem is the presence of what for the coefficients? That notation means, of course, yeah, and choose k is what you're seeing here. And so when I said that we were turning away from combinatorics for a second, no, we're still here, and this belongs here, even though it feels like we're doing algebra. We're actually still doing combinatorics right now. It maybe takes a little bit of work to explain why we have the binomial coefficients being combinations. So we'll say why that is here. We'll also expand a plus b to the 6th. As you expand a plus b to the 6th, try to do it not from the previous, I know it's in your notes there, so you can already say what it is from the previous just out loud probably, because you have a plus b to the 5th written there in your notes now. But see if you can do it tracking this theorem here, right? Does it work? Does it make sense that we get 6 choose 0 times a to the 6th b to the 0 plus, keep going, 6 choose 1 a to the 5th b to the 1st plus, and keep going. So in this first step, of course, we just get a to the 6th. 6 choose 0 is 1, b to the 0 is 1, so you just get a to the 6th. Right, but actually kind of think of this, and is this what you're getting? Does it make sense in terms of what we just did with Pascal's triangle, that they agree? Yeah, the next one.
I was just wondering what the k value is. Like I see that it says a to the n minus k and then b to the k.
The k is some value in the middle. So say you want some value between 0 and n, right? So if you want the, in this expansion, you want the fourth order term. Well, then you're doing n choose 4, or 6 choose 4. A to the 2, b to the 4, right? You want the right. Right, so in the middle here, what do we get here? 6 choose 2 is, what do you get there? 15? And 6 choose 3? And now we see from the warm-up today too that this is of course the same stuff as we march down. On your calculator, this may be a new calculator trick for you. You're welcome to try this. This is our answer here. If you get out your calculator and type in 6, C, and then in curly braces separated by commas, 0, 1, 2, 3, 4, 5, 6. And press enter, it'll do all of those at once. It'll give you all the coefficients at once. Try that. So type in 6 and then NCR, and then in curly braces, separated by commas, the number 0 through 6. It'll just give you, as an output, 1, 6, 15, 20, 15, 6, 1, right? In general, on your calculator, anytime you want to do that, like if you want to graph like 3 lines, you can graph like y equals 2x plus curly braces 0, 1, 2, 3 or something. It'll graph 3 lines, you know. So everyone your calculator, this works everywhere on your calculator. To use like curly braces, it'll evaluate whatever you're doing for all the values. Yeah.
I think I'm missing, like, what's the point of doing, like, the combinatorics if you could just do
Use
it?
Pascal's triangle, you mean? We'll say the next. Or,
Like writing it like that way with like the, like the 6 over the 0 and 6 over the.
you mean like you'd just like to do this from the last slide just by expanding it after a plus b to the 5th?
Yeah.
All right, well now do a plus b to the 12th. Go ahead.
But then you have to break up the triangle.
Yeah, you'd have to write the whole triangle. You wouldn't here though, would you?
No.
Right, you could just start writing them down. Now, it still remains to be seen why these combinations are topping up. So let's actually work this out here. Imagine you're doing a plus b to the 6th, and you wanted to do it longhand. And you hadn't done any of the previous ones, right? That is, I want to do a plus b times a plus b. So I'm going to do a very loose sketch of a proof for why this kind of works, right? That you're getting these combinations in here. I get 6 of them, good. So imagine you're forming this product by hand from this original expression. How would you do that? Well, in some ways it's kind of super FOIL, right? It's like, I want to get everything. Have you ever, whenever you do FOIL, some of us just don't do FOIL. We're just like, I just need to multiply everything from this set of parentheses by everything from this set of parentheses and make sure I don't miss anything, right? Isn't that how you think about it? Well, the same thing can be said here. Just multiply everything by everything you can multiply by, right? So like multiply this A by this B, and this A, and this A, and this B, and this, right? Make sure you get them all, right? All right, so let's start thinking about what could be gotten and how many of them, how many ways you could get that thing. So for example, how many ways are there to get an a to the 6th from that? Well, of course, there's only one way. Choose this A, this one, this one, this one, this one, and this one. But how many ways are there to get 5 A's and 1 B? You could choose these 5 A's and this B, or you could choose these 5 A's and this B. Well, it's pretty clear that there are 6 different B's that you could pick to go with your A, with your 5 A's. All right, what about, now it gets a little trickier. How many ways are there to find 4 A's and 2 B's? Okay, well, you could select this one and this one, and this one and this one, and these 2 B's. Or lots of different ways. You can even say, how many combinations of 4 A's can you find from this set of brackets, right? And of course the answer is 6 choose 4, right? Or 6 choose 2, whichever. Because choosing 4 A's is the same as leaving 2 B's on the table, isn't it? So, whichever. 6 choose 2 is, I guess, how we wrote it here, whichever. You see how this works and why that comes out? Let's also try and quickly form a connection with Pascal's triangle just for fun. Here's a fun game. Say you're a little person and you have rules in life, and your rules are I can move down 1 step. You can always either move down to the left or down to the right. So how many ways are there for you to get to I don't know, this position right here, or given those 2 rules that you can move always down to the left or right? You can go. So you could go. That's one way. How else could you get here? Yeah, and good. How many is that? 3 ways to get to that point. 1, 2, always down and to the left or down and to the right. 3. How many ways are there to get to this point? This point? And this one's 2. 1, 1. This one's 1, 1, and that's of course 1. So you can see why maybe as we traverse a lattice, why we get combination as we get, and all the binomial coefficients appear as we traverse a lattice as well. So, and there's so much more we could say about those connections, but I think that suffices for that. Okay. So let's, it would be, I think, a little bit too much to ask someone to expand all the way, x plus y to the 15th. How many terms are in that expansion? Good, 16, right? There's 16 terms in that expansion. You always get like n plus 1 items, terms. So I think it's reasonable to ask for this. Let's first verify that this is a reasonable question to ask. Is there an x to the 12th? y to the third term somewhere in that expansion? How do you know that there is? Yeah,
Because 12 plus 3 equals 50.
it's got to be somewhere in there, right? So we are giving you the variable part. The question is, what's the coefficient? Well, after the last slide, we know that the coefficient of that will be some combination, right? Something choose something. What is it in this case? Yeah, 15 choose, yeah, whichever you like, right? So that's the coefficient, and we're going to be done with this problem. What does that come out to? 15 choose 3 is?
455.
So find that term. We have done it. So we didn't do the whole expansion, but if you were, you would see that in it. Okay? All right, down here, this is a complicated way of asking. In this expansion, what's the cubic term? What's the m to the third term in this expansion? Let's just think about this expansion for a second. In some ways, having a number in there is harder. You prefer like a plus b or x plus y. Having a number there is a little messy. But let's just verify that if you were to multiply this out, let's not. It would be m to the 13th plus something times m to the 12th plus something times m to the 11th all the way down to a constant term, right? So is there an m to the third term in there somewhere? Yeah, there is. Well, what's its form? M takes the role of like x, right? So that's m to the third. And negative 2 takes the role of like y, right? So it's m to the third, negative 2 to the, they need to add up to 13. But we also need a binomial coefficient. And for us here, power is 13, what choose what? Yeah, 13, choose 3 or 10, whichever, doesn't matter. Okay, they're the same. Good, so we haven't finished here. We need to actually say what this is here. But notice here we don't just need to type in 13 choose 3, we also need to figure out what negative 2 to the 10th is and multiply with 2, right? So what is 13 choose 3? Anyone have that yet?
286.
And negative 2 to the 10th, maybe we know that off the top of our head. Positive 1024. And multiply those, and we'll have our m to the third term, or m to the third term. What times m to the third? What do we have? 286 times 1024. 292,864. Confirm. Someone? Okay. So in the way the question was asked is like, what's a? Well, I guess a is this coefficient 29. Okay, let's repeat this kind of thinking as we go to get the 6th order term in this expansion. Certainly there is one, m to the 6th, negative 2 to the what? And the coefficient up front will be 13 choose whichever again you like, 6 or 7. Okay. And now type in both of these things here. We need 13 choose 6. Excuse me. Negative 2 to the 7th is, what's 2 to the 7th? And again, maybe you know that off the top of your head. It's 128. Well, it's not 128. It's negative 128, right? So the coefficient here comes out to be something negative. So what do we get in the end there? What is 1716 times negative 128? So what's b? I guess b is that number. Keep in mind that it's negative. I want to show you both so you can see that there's another observation to make besides just saying, oh, this is m to the 13th plus something times m to the 12th plus something times m to the 11th. Yes, of course it is. But it's also true that we get alternating signs throughout this expansion, right? We get m to the 13th minus something times m to the 12th plus something times m to the 11th minus something times m to the 10th, alternating back and forth. All the odd ordered terms have a positive coefficient. All the even powers have a negative coefficient. So do this one right now. Go ahead. I'll give you 2 or 3 minutes to work this out. Already, this will be a, can you see that this will be a 10th order polynomial, right? So write up, do the whole expansion on this. Go ahead. Do it carefully, thinking about with a roll of the 3 in particular, and the 1, how that all works. We'll come back together in a few minutes. Just check with your group here. A few minutes to do that.
What's 3 to?
How's it going? This is, how you doing? This is GeoGebra. You guys have used GeoGebra, right? You've seen me use it maybe. It has a computer algebra system built in. You can also do it on Wolfram Alpha if you like. You can ask it to expand 3p squared plus 1 to a bit. All right, ready to check your answer? See if this is what you got. Yeah? So we got a 10 to 3 polynomial, p to the 10th, p to the 8th, no odd powers of p. Okay. Anyone need any help explaining where one of these numbers comes from? You got powers of 3 times binomial coefficients all along the way, right? See if we can do one more before we go, maybe. This is worth talking about. I like this one. This is probably the trickiest problem I'll throw out you today here. X equals 1 times X equals 2 to the 10. Now we're getting crazy.
It looks so good.
Well, one way to do this, of course, would be to actually multiply out 3x plus 2 to the 10. It's worth actually saying what that is, baby, here. It's x times 3x to the 10th plus 3x to the 9th, 2 to the 1st, times 10, choose 1. All right, well, it's this long thing, right? We don't need to write that out maybe, but I think it's helpful to kind of think about what would you actually do next if you were to actually think about the actions you would take. After you would resolve that whole thing, God forbid you'd actually do it. Then how would you multiply by x plus 1? What would you actually do? Everyone turn to your neighbor and tell them, what would you do after you finish doing this part over here? How would you multiply by x plus 1? Like actually, what would you do? All right, what would be your way of doing it, Ashley? I mean, if you were to actually do this longhand here. Yeah, because you're multiplying everything by 1 also, is what you're saying. Yeah, everyone, I think that's what probably most of you said. You're going to multiply everything by x, store that in your head, multiply everything by 1. I love multiplying things by 1. And then collect like terms, right? Okay, so now the ultimate question is none of those things. The ultimate question is, can you just tell me what the x to the 6th term would be in that expansion? Now think about the things you've done. You've multiplied by x. Which term of interest is there over here to you when you're multiplying by x? Yeah, the term where x to the 5th appears. And when you're multiplying through by 1, what term is of interest? Yeah, so I'd like to maybe just more closely examine in the middle of this. I think I don't care about anything else. But in the middle of this, there's an x to the 6th term and an x to the 5th term, which I care about. So let's see if we can find those. The x to the 6th term will be of the form 3x to the 6th, 2 to the 4th, 10 choose 6 or 4. And the term right after that I'm interested in too. Then choose 7, whatever. 3x to the 5th, 2 to the 5th. When we multiply through by x, this term will be 10 choose 7, 3x to the 5th, 2 to the 5th times x. That will be a 6th order term. And when we multiply through by 1, we have already this term, right, that we already had that was of order 6. So if we add these together, we have these are the two like terms that we would have gotten. Everything else doesn't matter. These are the two like terms that carry an x to the 6. So we need to like resolve all this nonsense. And we need to resolve all this nonsense and add them together. And if someone has that, that would be great. It'll be something in the end times x to the 6th, right? Anyone have it? What's that? What did I say? 10 choose 6? Sorry. All right, here's the answer. Right there. I know, yeah, I heard you say that. Better?
Wednesdays, but apparently that was trying to explain
What did you see there? Where am I? Which one? This one? Oh, 10 choose 5. All right, I think everything else is okay.